Faraday's Law. It says it right there, chapter 22. So I am working through chapter summaries for matter and interactions, and I'm on chapter 22. Now, this is Faraday's Law, but there's a whole bunch of stuff that's kind of accumulated up to this point. Let's just talk for a second. Remember this, a point charge. The electric field, is that out of focus? Stop, focus, okay. The electric field due to a point charge, does it get out of focus when I do? Okay, that's fine. So it looks like this. It radiates outward from a point charge. That's the electric field. We can call this shape of a field where it points away from positive charges and towards negative charges. This is a Coulomb field. Okay. Now, we also have a moving point charge. So imagine that I have a point charge and it's coming out of the paper right there. QV, it's positive QV coming out of the paper. So that's a vector coming out of the paper. Then in that case, we would make a magnetic field that looks like this. That's B. This is E. So we call this a curly field. And I didn't invent those words, Coulomb field and curly field. They're in the book. But is it possible to make an electric field that looks like this? And the answer is yes. And that's what Faraday's law is all about. Okay, so let's just review the other two laws that we have before, the important ones. We have this, Gauss's law. This says that if I take some surface around this charge, then I could calculate the electric flux. That's what this is, the electric flux over a closed surface, and that depends on the total charge inside. Now, if you set this up in a reasonable situation, you can actually use that to calculate the electric field, but you'd have to pick a surface that's easy to integrate. And then we have Gauss's law for magnetism. And this just says it's the same thing, but we use magnetic field, B, instead of the electric field. And this says that there is no magnetic charge because the charge inside of the surface, the magnetic charge is 0. So that's that. Okay, let me go ahead and write down Faraday's law. So Faraday's law is how to create a curly electric field, or as the book calls it, it would look like this shape. How can we make that shape of an electric field that looks like that? And they call that ENC. That's the non-Coulomb, right? Because that's a Coulomb field. You cannot make a field like this with charges. You can't. But you can with a changing magnetic flux. So remember what flux is. Okay, so I can write flux, the magnetic, let's do the electric flux, over some surface. It's E dot n hat dA. And if you want to represent that, this flux depends, that's not a closed surface. This flux depends on the vector value of the electric field. N hat is a unit vector perpendicular to that area, and then this is the area. So if I integrate over that whole area, I'd get E dot n hat A times A, and that would be the flux, the electric flux. Well, you could do the same thing for the magnetic field. The magnetic flux is the integral of B dot n hat dA. Okay, let's write down Faraday's law. Faraday's law looks like this, and it's kind of important. It says, I don't want to write in that corner. If I write in that corner, it gets fuzzy. Not sure why. Okay. It says this. I'll write it like the book does. This is a path integral of E dot dl. Remember before in our circuits we said that the electric field integrated over a closed loop was 0. It's not 0 now. It's equal to negative the derivative with respect to time of the magnetic flux. So this says that if I have some region in space like this, and I have a magnetic field going into the board, into the paper, and that magnetic field changes, then this will create, let's see, that would create, let's say if the field turns off, this will create a magnetic field, an electric field going this way. This will make a curly electric field. So there's two ways to make electric fields. I can use charges or changing magnetic flux. And this is Faraday's law. So we have a time derivative, right? And so this is important because how do I change the flux? Well, I could change the value of the magnetic field. I could change the angle between B and N hat, or I could change the area. So if you take this this loop and squish it, that would induce a changing electric flux around that changing surface area. But that is Faraday's law. Let's go ahead and talk about Lenz's law, because this is really a difficult one to grasp. Lenz's law is about that negative sign right there. And this says that if you make a curly electric field and it made an electric current, that electric current would make a magnetic field, and that magnetic field would oppose the change in flux. Okay, so let me give you an example. Suppose I have a loop right here, a loop of wire, and I have a magnetic field going into there. So it's B1 into the paper. And then that goes to this situation where I have 0. There's no magnetic field. B2 equals 0. So I had a magnetic flux going into the paper, and then I had none. This is going to induce a current, and the current wants to maintain the flux, right? So the current induced in here wants to keep the flux going in the same way because it's decreasing. So if I have, how would this make a current going into that would make a magnetic field going into the loop, into the board? Well, you can use your right-hand rule. If I put my hand in the direction of the current this way, it would make a magnetic field going that way. So that would kind of try to maintain the magnetic field and the magnetic flux. Now, let's say that I turn the magnetic field back on. So I go from here to here, back in the same direction. So B3 is into the board. Now I'm going from no magnetic flux to magnetic flux in the direction of the paper, and this would want to oppose it. So it would go that way to make the magnetic field that would oppose that change. So this is oppose the change. No change. Of course, it always loses, but that's how it works. And so you always want to think, which way would this current have to be to prevent the change in flux? It can get a little tricky. Okay, let's go to another example of Faraday's law that we already did. So we had this thing called motional EMF. So remember, if I had a resistor and 2 wires, and then I had a bar like this, and I have a magnetic field going into the board, like that. And this has a length L. And if this is moved with a velocity v, we found from the previous case, using the Lorentz force, that the EMF across there would be it'd be VLB. Right? The velocity of the stick, how fast you move this, times the length of the stick, times the magnitude of the magnetic field, and assuming this area is perpendicular to the magnetic field. Okay, so we did that already. Now let's do it again using Faraday's law. So imagine that I take this same thing and I have my stick right here, and then it gets moved over here. So if this is my area, you can see that I'm increasing my area. If I have a magnetic field here, I'm increasing the flux. So one way to write Faraday's law, this, is to say this is EMF, right? That's the non-Coulomb EMF. That's the flux, and that's the rate of change of flux. And we're just going to deal with the magnitude for right now, but I can write this as EMF is going to be equal to the derivative with respect to time of the magnetic flux. That's the same thing. That is Faraday's law. And if I write the flux in this case, since the magnetic field is in the same direction as N hat, right, because it's perpendicular, then I can write this as the derivative of the magnetic field times the area. That's true because B and N hat are in the same direction. I don't even need to integrate. Everything's constant. I just get B times A for the magnetic flux. Now, what about if I think about some time interval delta t? In some time interval, what's the change in area here? Well, the area goes from something to, we'll call this delta x, where delta x is going to be equal to V delta t, right? If I have some time interval delta t, that's how far it's going to move. V delta T. So the change in area here, delta A, is going to be delta X times L, which is going to be V delta T L. That's the change in area. Now, if I use that up here, I can write EMF. It's going to be, I'm going to write this as a finite change, delta BA over delta T. The B comes out, doesn't change. Delta A is this, which is V delta TL. I divide that by delta T. Oh my gosh, look what happens. And I get B VL, same as before. So we can explain this idea of moving a bar through a magnetic field using Lorentz force. Remember, this was saying this is going to move charges such that F equals QE plus QV cross B. And then that create an electric field in here, and the electric field will produce a change in potential. That's what we did before. Or you could use Faraday's law, and you get the same thing. Okay, so, and you know they have to be the same thing because you could actually measure that voltage. It doesn't really matter which way you do it. The voltage is the voltage. Now, the same thing happens. You could also think of this Faraday's law for a rotating coil. So suppose I have a coil of wire right here. I'm going to draw it as a square. And it's rotating about this axis right here. And there's a magnetic field going down. And this has an in hat like that. You can't even see it. So as this coil rotates, the flux changes, right? So again, I can say EMF is, let's write it as a derivative, d phi dt. So if this is rotating at some angle, then I can write this as the derivative of BA cosine theta, where theta is the angle of that. And then if A and B are constant, I can factor those out, and I get EMF is B A, and then the derivative of cosine theta is going to be equal to negative sine theta. But then I have to take the derivative of theta, which is d theta dt. And d theta dt is the angular velocity omega. So it's going to be, I'll leave off the sign, B A sine theta omega. I mean, but the point is that rotating a coil produces a change in voltage. And this is really important because most of our electric generators work this way. You can take a coil of wire, you apply it in a magnetic field, then you rotate it, and you get an electric current. Okay. And the question is, how do you make that rotate? A very common way is to have a turbine. So like here, we'll put some fans up here, like this, and then I'll have steam come up there and push it and turn it. And then the question is, how do I heat up that steam? That's fire. I could take some fossil fuel and burn it, and that would make steam, turn the turbine, generate electricity, but then you end up with carbon dioxide, bad. You could have wind turn the turbine, good. You could have falling water turn the turbine, good. You could take a nuclear reaction to heat up water and make steam, and then you don't have carbon dioxide. Okay, moving along. Let's look at inductance. So I just want to remind you about capacitors, because capacitors and inductors go hand in hand together. So remember that if I put a capacitor in a circuit, with let's put a resistor in there, then as the current flows, charge builds up on this capacitor until the charge on the capacitor produces a voltage equal to EMF and there's no current. So this does not like constant current. It'll stop the current from flowing. Now, if you had an alternating current source, you'd put charge on, take charge off, take charge, and it would never fully charge up, and it would not equal the potential over here, so you'd still have it behaving. And in fact, if you have a high frequency source, this acts like it's not even there. At a low frequency, it acts like a short, like a break. Okay, and that's a capacitor. Now, an inductor is basically just a loop of wire. And the best way to represent this is a loop around a solenoid. Now, I didn't derive it, but I'm going to go ahead and tell you that the magnetic field inside of a solenoid is constant. And we can write that as mu naught, what was the equation? Mu naught N I over D. So this is D, the length of the wire. And N is the number of turns. I is the current, and mu naught is the mu naught. So that's the magnetic field inside of a loop of wire. Now let's say that we have a current coming in there and a current coming out. Let's imagine that I have this loop at the beginning right here. It's going to make a magnetic field that's going to produce a magnetic flux over here. Right? This magnetic flux field will make a magnetic flux right there. So let's calculate the magnetic flux due to this wire. So the flux is going to be equal to the magnetic field, which is this, right? Because it's actually due to all the loops. So it's mu naught n I over d. And the flux would be that times the area. But then I also have in things up here, right? I have in things that get flux. So I actually get another n. So I can write this as mu naught n squared d a I. Faraday's law says that if I change the current, I'll change the flux and I'll produce an EMF. So I can say Faraday's law says EMF across the capacitor is equal to, and I'm going to leave off the sign, we don't have to worry about the sign, the derivative with respect to time of the flux. So let's put this in for the flux. I get the derivative with respect to time of mu naught n squared a over d I. And all of that stuff is constant with time. The only thing that could change with time is I, so I can pull that out, and I get mu naught n squared a over d, and that's the d is the length of the cylinder, and then the derivative of current with respect to time. So this tells me if I change the current, then I'm going to get a voltage. Very similar to up here is if I have a charge, I'll get a voltage. Remember, delta V's capacitor is Q over C. We did the similar type of thing for the capacitor. But here I have this change in current. And I have some constant stuff out front that depend on the parameters of the cylinder, mu naught n squared a over d, and we call that the inductance. So L for a cylinder is mu naught n squared a over d, and has units of henries. Henries. I think that's how you spell it. And that's the inductance. So I can write the potential across an inductor, delta V L is L di dt. So now we have a device. Over here, the capacitor has a voltage that depends on the charge, and here we have a device where the voltage depends on the change in current. And notice that, remember that current is the derivative of charge. So this is, if you turn it into charge, you have charge and then the second derivative of charge. And you can do a whole bunch of really cool problems with that. I'm not going to do those right now, but that is what we're going to do. Oh, a lot of times I'll write this A as pi r squared because it's the area of that circle. Okay. But remember, there's double n's there because each coil affects each other coil. That's why you have double that n squared, number of turns. We have another example of, I thought it wasn't recording for a second. What the heck? Okay. Another very useful example of an inductor is what's called a transformer. And, you know, if you grew up in the 90s, which you didn't, probably, you know, you think of the Transformer robots. That was actually after my time, to tell you the truth. I didn't really do Transformers, but that's just a Transformer joke. So imagine that I have a loop, a cylinder, and then I put another cylinder over that, like that. So this cylinder is going to make a magnetic field that's going to produce a flux right there. So let's call this, let's say that has N1 turns and that has N2 turns. So the magnetic field in this loop, in this inner loop, B is mu naught N1 I over D. That's the magnetic field due to a solenoid. And the flux is going to be in this outer loop. The flux is B times A, which is equal to B times the area of one loop, I'll just call that A, times N2, where the number of every loop has its own flux. So now if I take the derivative of this with respect to time, I get the derivative of the flux with respect to time for this outer sphere. It's going to be B, which is going to be this, mu naught N1 I over D, that's B, A N2. Did I do that right? And, oh, I got to take the derivative of that. Sorry about that. Well, the only thing that changes with time is the current, so I can write this as mu naught N1 N2 over D A di dt. Okay, where did I go with this? And this is the EMF. That's the EMF around this loop. What's the EMF around the first loop? Okay. I think that's what I do. I'm confusing myself here. Where did I put this? That's the inductance. I thought I worked this problem out. Okay. I'm getting myself stuck here. I got a little confused. Okay, so that's that EMF. What's the EMF across this? Well, EMF 1 is going to be equal to the change in current also, right? It's L di dt, where this is the inductance of that inner loop. Well, I already have an expression for the inductance, which is mu naught N1A over D. So it's going to be equal to mu naught N1 squared A over D di dt. But this is EMF 2. Where do I... they're not equal to each other. I messed this up. I'm not going to redo the whole video. Okay, let me look it up real quick. I'm going to use the book. Let's just look it up, and then I'll make a separate video deriving this. EMF. The point is the following. I feel bad. Okay. If you're watching this, I should cut this out. And I'm not gonna, because I just don't wanna. Inductance, I did that. Transformers. Okay. Oh, they're EMF 1. Okay, so you get this. EMF 2 equals N2 over N1 EMF 1. That's the important thing. We can write that. I can, because I have that same expression, I can put that over here. Okay, and this is the whole idea of a transformer. If I have, it's a way to change voltages, right? If I have N2 is very small compared to N1, voltage 2 is going to be small. So I can do a step down transformer. I can take a high voltage and get a low voltage from that. I can do the other way. I can make more turns on this, and then I could have a step up transformer. So I can take a low voltage and get a high voltage. But this depends on having a changing current. You have to have a changing current. Okay, that's important. But they turn out to be useful in all sorts of situations. If you take an old power plug, like, well, this is a new one. But if you take an old DC power plug, there, if you take them apart, you have these coils of wire in there. And I'm sorry I messed that one up. I apologize. I'm a bad person. Okay, moving along. Let's look at the energy density in the magnetic field. So if I probably did this before, if not, I'll make a separate video. If I have a capacitor like this, I make a constant electric field and we pull it apart, you can find the energy density, UE, as 1/2 epsilon naught magnitude of electric field squared. That's the energy density. That's the energy per unit volume in the electric field. We can do the same thing with a magnetic field using a solenoid. So remember that if I have a current coming in here, then I can find the power from any device, power as I delta V. So it's the current coming in times the change in voltage across that. That will give me the power, which is equal to the change in energy per time. Well, what if I put the voltage across this inductor as L di dt? So the power is I, and then I have L di dt, right? It's change in current. Well, if I want to find write this as the change in energy with respect to time, that is power, I can actually write that as dE dt. So let's solve for dE, the change in energy. Well, if I multiply both sides by delta t, which you can do, I get dE equals I L di dt dt. And you'll notice the dt's cancel. That's kind of nice. Now I can integrate both sides, and I get delta E, the change in energy, is going to be equal to the integral of L di dt, which is I squared over 2. Now I can put in my expression for the inductance of an inductor, L. And remember that L equals, where did I put it? This, mu naught n squared A over D. L is mu naught n squared A over D. So if I put that in right here, I get delta E equals mu naught n squared A over D, and then I have a 1/2, and then have I squared. Okay, now let's put in, let's just divide by the volume. The volume of the solenoid. Well, if this has a length D and an area A, the volume is going to be A times D. So this is going to be equal to 1/2 mu naught n squared A over D divided by A times D. The A's cancel. And then I have that I squared. So it's going to be equal to 1/2 mu naught n squared over D squared. Now let's find the magnetic field of a solenoid. Remember that B is mu naught n I over D. So over here, if I want to get that, over here I can, let's write this as 1/2 1 over mu naught, oh, there's an I there, I squared. Mu naught squared n squared I squared over D squared. So this right there is just the magnetic field squared. So I get 1/2 mu naught 1 over mu naught magnitude of the magnetic field squared. And that's the energy density for the magnetic field. And so this, along with that, is very important, right? Because this says that there's energy in the electric field, there's energy in the magnetic field, and that's important for light. We'll get to that when we talk about light. Okay, where am I now? I think that's it. Let's just write down Maxwell's equations again, and then we'll be done. So Maxwell's equations, we have Gauss's law, E dot n hat dA equals Qn over epsilon naught. We have Gauss's law for magnetism, B dot n hat dA equals 0. Then we have Faraday's law, which says that this is E dot dl, right? So it looks the same, we write it the same, but this is a path integral. That's a flux, a surface area integral. So the integral, the variable is dA. Here it's dl. This is a path integral. And it's not equal to 0. It's equal to negative d dt b dot n hat dA. And you'll notice here that this looks like that. But that's a closed surface flux integral. This is just the flux over a surface that's bounded by this path. So these two paths this path has to be the same as the boundary of that surface, but it's not a closed surface. And also, if you have no changing flux, if ddt of this flux is 0, then this becomes 0, which is what we had before. That's the loop rule. Okay, so those are our 4. Now, the last equation we have was this. I'm going to write it right here. B dot dl equals mu naught In. That's Ampere's law. And in chapter 23, spoiler alert, preview of the next thing, there's another way to make, this is a Coulomb field, no magnetic Coulomb field. Curly electric field, curly magnetic field. And there's actually 2 ways to make that. I can make that with a current passing through the surface bounded by this line integral, or plus mu naught epsilon naught d dt E dot n hat dA. Look at that. So I can make a curly magnetic field with a current or a changing electric flux. I can make a curly electric field with a changing magnetic flux. I can't have, why is there not a term like this up here? Because this, in order to have a term like that up here, I would have to have a current of magnetic charges, but we don't have magnetic charges. So if there were such a thing as magnetic monopole, this would not be 0 and there'd be another term here. But there's no such thing that we've seen. Maybe you'll find it. I don't know. Okay, so there was a lot there. It's very confusing. I know, and I messed up on the transformer thing. I know my own mistake, but hopefully you made it to the end. And I have one more chapter to do, chapter 23, and then we'll be done with the semester, and it's going to be great. Okay, the end.